Okay. Good afternoon. You have to realize I just finished my coffee break in Vancouver. But it's very nice to be in this part of the country today and to share with you some of the work that we have been doing in British Columbia. And it's not only the work that the University of British Columbia has been doing, but also the collaborative work that we have been doing with the Geological Authority of Canada, National Resources Canada, and the other universities as well, and as well as the provincial government. So what I'd like to cover in this presentation are three topics, as shown there. Similar to what has been presented already, I want to talk about the seismic risk in BC. I'd like to give you a snapshot of where are we in terms of understanding the seismic risk, the work that we have been doing, and how are we understanding the potential effects of the earthquakes that John Adams and Gail talked in the morning. The second topic is a new topic that has become quite important in the recent years. The government of Canada has been very, very interested in that. In fact, a number of years ago, they funded a project in developing the interdependencies between critical infrastructures. And I'm going to give you a short summary of what we have been doing, how we understand this concept, and why it's so important to start looking into this aspect as we are moving along in developing the science and the knowledge base that we have. And the last topic is one of the most exciting projects that we have in BC now that is related to real-time monitoring of earthquakes, notification and information that can be used by people that are interested in understanding earthquakes. Okay. So the first topic is risk. Okay. There are many ways of looking at the risk, but if we just look at the risk in two simpler components, the vulnerability of the buildings and the hazard. Okay. And we have been talking about the hazard in different regions of the country this morning, and we understand that we have earthquakes, where they are, the type of earthquakes that are occurring in different regions of the country. And also, but that's not enough just to say that we have a seismic risk. Okay? We have to bring the inventory of infrastructure. I'm talking about buildings here, but that can also be related to bridges, dams, nuclear power plants, etc. All the built environment will have a certain level of vulnerability. Okay? And the combination of the two is what comprises what we call the seismic risk. Okay? So how do we deal with this problem? First, just to summarize what we saw in the morning, we look at the probability levels of earthquakes and when they are occurring and the likelihood that they will occur in a certain region. Okay. Then we associate that with certain level of peak ground acceleration, which is a parameter that engineers have been used for a number of years as a design parameter, or another measure of the intensity of the shaking, the old traditional Mercalli intensity that is related to what is the level of damage that has been observed in a region. And today we have technology to associate the measure of motions that we have, as Luke was talking about what he measured in Montreal in the last earthquake, and associating that to the level of damage that is expected in the region. Okay. Then you bring up your inventory of buildings or infrastructure that you have, combine the two, and then you develop your actual indicators of risk, which we call the damage tables. Okay? Different stages of damage. A building could be very likely damaged that people will be able to go back into the building and keep using that. We will call that 100% functionality, or today the earthquake happens and tomorrow you can be at the building or using the building for whatever you need. Or it could be that the building is severely damaged not only because of the structural components failed, or the structural components didn't fail, but the interior of the building is a mess. Okay? And you cannot use the building because the building is not occupiable. So this is what we call the damage tables. And then you summarize that in information that is used by the different people. It could be in terms of percent of damage, the cost of repair of the building, human losses, casualties, etc. All of these are different indicators that we have to associate the risk. Okay. Here's an example of recent studies, or a number of studies that we have done in BC. This is, of course, Vancouver. And first, we have developed a building inventory. And this comprises about 25,000 buildings that have been cataloged one by one. And then we developed these thematic maps that show the distribution of the material that controls how the building will behave. For example, we'll have here concrete, masonry, steel, tilt-up, etc., stuff that engineers will love to have. And then we start seeing what regions of the in this case, Vancouver, what is the type of material that dominates the construction. Okay? So that builds the inventory. Okay? Then we apply an earthquake, and in this case, we assume that an earthquake has happened and it generated an intensity 8 in the Mercalli level. Okay, an intensity 8 of Mercalli level really shows that there is going to be some severe damage. And then we start seeing the maps of distribution of damage. In this case, is as a percent of the cost of the building. If the building costs $10 million, 10% will be $1 million in repairs of that. And then you start seeing the distribution of damage at different levels on the cost, and then you can aggregate all of that to get an idea of how much will cost you to repair your buildings in that region. And of course, then you start seeing areas, or what you call the hot spots. The red colors are areas where there is more significant damage than others. And in this case, it's clear, those of you who are familiar with Vancouver, this is Gastown. It's an area where we have old buildings, and old buildings usually don't perform very well. And some of those buildings have not been retrofitted, and then you have the consequence there. But then you start looking at the overall picture of what had happened. Darius talked about the soil conditions, the importance of that. And we can start bringing this into the model. Here's an example of Victoria, where first we do the analysis assuming that the soil conditions are uniform across the lower mainland and in the central regional district. According to the building code, site class C is the classification that we assume that the whole Canada is building that type of soil. But the reality is that we have different soil conditions. Even in this small area in Victoria, you can see the variation of soil conditions. And of course, the soil conditions, the red ones are the ones that are more critical because of these types of soft soils. So I superimpose that effect in my map. And then what I have now is a comparison of the expected damage that I will have without considering the soil conditions and considering the soil conditions. Okay? So I can immediately start seeing the effect of how important it is to consider site conditions in the expected performance of buildings, and for me to get a better understanding of how the damage is going to be distributed to the region. And of course, you see that our provincial government resides here, and they are not in good shape. Okay. Then we start looking at how these monetary losses are distributed. Where are they coming from? Okay. And this is a study done by Professor Miranda at Stanford that pretty much summarizes where the cost is coming. Okay. So here is an example of typical office buildings, hotels, and hospitals. Okay. And although we engineers will always concentrate on the structural damage, you can see that the most significant contribution to the cost of repair is the non-structural components, the inside of the building. What's in there? I would say in general about 75% of the cost is associated to repairing inside the building. Okay. So where is that coming from? From lessons learned from past earthquakes. Studies that have been done looking at the damage distribution. And then you see, for example, in a hospital, that the non-structural and the contents become very important, because if they fail, although the hospital might be seismically adequate or may have been retrofitted, if the contents fail, you cannot use the hospital. Okay? The hospital will not be operational, and that's not acceptable. Okay? The hospital has to remain operational after the earthquake. So this is how we are learning more about this distribution. Okay? Then we start looking more carefully at what are these non-structural elements and how they fail. And some of those structural elements are more sensitive to the level of shaking in the building. Others are more sensitive to the displacement between the roof and the floor and the ceiling. Okay? And if you just look at the doors here, and we have an earthquake and the door will jam, it's because the ceiling moved relatively to the floor significantly, and the door is jammed. Okay? That will be called a displacement-sensitive component. Whereas, for example, the sprinkler systems or the air conditioner and everything that is hanging from the roof here is more sensitive to the level of shaking of the acceleration. And it will be damaged not because the roof is moving or the ceiling is moving, but because it's moving very fast. Okay. So now we can see the sensitivity of these components to the level of shaking. Okay. And the rest is the contents, the desks, the tables what we are using, how they are damaged. So we start seeing that at some point, the significant contribution to the damage is coming from the elements that are displacement sensitive. Those are the ones that are going to be most costly to repair. Okay. Then we also can look at how a building will remain or will be functional after the earthquake. And this is a study that we did for the UBC campus. I'll address that in more detail later on. But then we start seeing, out of the total number of buildings on campus at UBC that we catalog about 450 buildings, we start seeing which buildings are functional and not functional depending on the use of that. In our university, we have classrooms, we have laboratories, we have residential buildings, etc. So this comprises all that inventory. And of course, you can see that the red color, again, is a building that is not useful. Why is that? Either because it has very severe structural damage or because the contents do not permit the people to use the building. It could be a laboratory where there is a big mess in the laboratory and you might have an environmental impact or something like that, and that will be considered a non-functional building. So again, we start looking at the picture of at what point a good number of your buildings are not functional because of a number of parameters. Okay. An example of the collaboration that we've been having with different groups in BC, I'd like to share with you some preliminary results of this effort. And there is an effort in BC now to adapt the HASUS methodology, which is some of you might be familiar with. It's a methodology to do loss estimation in the United States. It's HAZARD US, it stands HASUS for. And we are currently working with the FEMA people in the US to adapt the HASUS methodology to Canada. And we have been using the West Coast to see what needs to be changed, adapted to the situation that we have. The building types that we have in BC are somewhat different than the ones that are built into this HASUS model, the soil conditions, the type of earthquakes, etc. But I just wanted to share with you this effort that we have, which is a collaborative effort between UBC, SFU, and Natural Resources Canada as part of that group. And we started tackling this problem. And the goal of this effort is to have, at the end, results that are very consistent. Not that UBC is providing results and SFU is providing results that might be contradictory. We try to get together, compare results, and then issue a consistent message to the people so people don't get confused. And we go through the whole process of developing the ground motions, understanding ground motions in BC, the building inventories. We have different levels of building inventories, starting from Statistics Canada, the information that is provided there that is very fast and easy to obtain. Maybe go to the provincial government and get information from the BC Assessment Office and get other level of information, or just hit the streets and do a survey of the buildings. Okay. We have all of those done. Okay. The examples that I showed you earlier were based on level 3 survey where we catalog all these buildings, and presently, including Victoria, Richmond, Vancouver, and the North Shore, we have about 150,000 buildings that it has been cataloged through this process. But that takes time. Okay. Whereas if we just go to the level 1 assessment, it's much faster. You just use information that is already developed. You accept that the information is not complete, that has drawbacks, but then you can start using to start seeing some information. Okay. So I'd like to show you some of the preliminary results that we have obtained through this collaborative effort for level 1. Okay. That information has been used, was used recently for a workshop that we have with TransLink. TransLink was concerned about their capability to respond to an earthquake based on what they saw in Japan. And of course, TransLink has its own emergency response plans, etc. But they were concerned about the ability to interact with the other groups like BC Hydro, the gas company, et cetera, telecommunication company, et cetera, whether they were talking about the same language and they could come out with a consistent effort in how to respond to an earthquake. Okay. So I'm going to show you some scenarios, but I want to have this here disclaimer because I'm going to show you some estimates of potential economic losses and other losses, but they are based on very simple models. They are of very preliminary nature, but the idea here is just to illustrate what we are learning and how these tools are working. Okay. So we look at, sorry for that, okay, at 3 possible earthquakes. One is, oops, let me turn this off because. One earthquake in the Strait of Georgia. There is another fault that's called the Kendall fault. We have a simulated earthquake here, and of course we simulated as a Cascadia subduction earthquake, and then we started seeing what will be the consequences of those earthquakes in the lower mainland. Okay. Right now we're just talking about the region here. Okay. So we go first and developing a shake map, an estimated shake map by, let's say, a Cascadia subduction zone, 8.2 in this case, and here is your distribution of intensities. The hotter the color, the higher is the expected level of shaking and damage that will be expected in that region. Okay. So I'll just go through this one. Then an earthquake in the Georgia Strait. Okay. Now you see how the colors are changing because we have, although it's a smaller earthquake, it's much closer to the urban areas, and then the level of shaking it will be more severe in the downtown area. And then the Kendall fault, although it's much farther away from Vancouver and Richmond, it was interesting to see what will be the potential consequences of that earthquake in there. Okay. So that's the hazard. Okay, and now we start building up the inventories. We also start looking at the soil conditions because, as I mentioned, they are important. And then we start looking at the whole lower mainland, the areas where we expect significant amplification of the ground motion as these ground motions are occurring. So we have maps like these that allow us to do that. We can also look at liquefaction potential because that's an important aspect for us, especially in the Delta region. Here, the red areas are areas where the potential for liquefaction is much higher. And typically, liquefaction will have a severe impact in infrastructure. And then we have to account for that effect as well. Okay, so here are some of the results. For the subduction earthquake, we're using the hazard methodology. And again, these are numbers that are very preliminary, but just for comparison purposes, about 70,000 buildings are severely damaged according to this scenario. And the economic losses is about $10 billion, of which 25% losses are estimated related to business interruption. Okay? And of course, the largest loss was made of residential construction. Okay? So it's not the tall buildings or the fancy buildings that we keep analyzing as engineers, are the regular homes that are going to be more problematic in this case. Now, if I change the picture and move now to the Strait of Georgia earthquake, now we're looking at the number of buildings has increased, about 130,000 buildings. The economic losses now have doubled because we have more buildings damaged. And again, the residential construction accounts for about 68% of the losses that we are incurring on that. And the third one, just as a reference point, the Kendall fault, of course, has a less impact because it's affecting an area that is less populated so far. Okay? And we are looking at about $1.5 billion in damage, about 10,000 buildings that have been damaged here. And of the area affected there, it's still the losses in residential construction tend to be very large. Okay. So this is what we are learning from these studies. What are the buildings that will have the most severe impact? And then what tools do we have to develop to control that risk and manage that risk? Okay. We also can look at the number of people affected by these earthquakes, and again, going through the 3 earthquakes that I was discussing. Here's a subduction event. About 15,000 people will need to have shelter. And about 25,000 households will be affected, okay? And then the question is, how long will it take for these houses to be repaired, okay? If people claim to have insurance, how long will it take for the insurance to pay for that, and how long is it going to take for these people to find a contractor to repair their homes, okay? For the large, closer earthquake, because it's affecting a more significant area, or we have about 41,000 households, of which 22,000 people are going to start looking for shelters. Okay? And comparing to the smaller, farther away earthquake, not smaller, but farther away, well, the numbers tell you this: 700 and about 500 people, less than 500 people being affected or needing for shelters. Another important aspect was the debris generation. Okay? The earthquake in Japan generated an incredible amount of debris. And in fact, people in Tofino and Euclid now are starting to see some of this debris reaching the west coast of Vancouver Island. Okay, people now are starting collecting, and in fact, in Tofino, people are starting to collect some of the belongings and try to put them together and eventually ship them back to Japan, right? So debris generation is very important, okay, to consider in the effects of earthquakes. And here are the estimates about, for this subduction earthquake, about 5.3 million tons of debris, okay, mainly from bricks. Okay, that means taking about 200,000 truckloads to ship that material somewhere, okay? Where, we don't know, okay? For the Georgia Strait event, now we're talking about 10 million tons of debris, okay? And again, about 400,000 truckloads to transport that material somewhere, okay? And for the Kendall earthquake, okay, again, a much smaller in impact, not necessarily smaller in size. We're talking about 0.3 million tons and about 13,000 truckloads. So I hope that this can give you an idea of the tools that we have. And of course, they have to be refined, the models have to be verified, but at least these tools are available now, and it doesn't take much time if you have all the information available. Of course, the information that I presented to you here was based on census tracts information, so that information needs to be verified to ensure that the model is working properly. Okay. The second topic that I have is tied up to the first one. Okay. So far, I've been talking about individual buildings or individual bridges failing or not failing or becoming operational. But what happens when we start looking at the domino effect? Okay. What if one infrastructure fails? What is the domino effect on the other ones? Okay. And this is what we call the interdependencies. Okay. And here is just a cartoon to illustrate the concept. Okay. That we, for example, we have electric power here. It's tied up to communications somehow. Okay. Communications needs power. Okay. And electric generation also needs communication. And that's the concept of interdependencies. And as you can see in this diagram, it's very complex. It starts becoming incredibly intricate analysis. And the question to us was, do we have a way to start looking at this problem, at least to start getting a sense of what happens? Okay. So this is how we did it. Okay. We recognize that there are interdependencies within and between infrastructures. Okay. Second, that the interdependencies are very complex relationships. Okay. And second and third one, that is a very time-dependent problem, that the dependencies at time zero immediately after the earthquake will be very different and than the interdependencies an hour or 2 hours later or a week later. Okay. So how we do that? Okay. We got together with a bunch of researchers at UBC in electrical engineering, computer sciences, engineering, etc. And we tackled the problem and say, how can we solve this problem? And we developed the concept that is called a simulator, similar to what the pilots do when they train for airplanes, that you simulate situations and the pilots are trained to react to that without crashing a real airplane. So we developed this simulator we call the I2Sim, and these computers essentially represent different infrastructures that are connected, interconnected. For example, in this case, we have a hospital, a power station, a steam generation plant, etc., how they are interconnected and how they are going to feed information to each other. Okay? So we use a concept that's called visual analytics. So we start bringing a lot of information and put it in simple ways to look at that. And this we call the production cell that will reflect. The cell could be a hospital or could be a substation. And that will depend on a number of parameters. And all these squares here are related to communication layer, the decision layer, the damage, production, etc. Okay? So then you start looking at in this model as, for example, at the water cell, information is coming from sensors, information is coming from being physically operational, okay? And whether it is 100% operational or 50% or 10% operational, and how is that going to affect other infrastructures, okay? So you start developing models like this that you have one cell connected to another one, but to transport information or the output from one cell that is going to be the input to the other cell, there will be other parameters that will have an influence on that. And this is terminology that we use because we are dealing with computer-sized people, and they like to do that stuff. This is the only question that I presented to you. And it's essentially how we put the mathematics in the problem. Okay? Essentially, what we are saying is T is a transpose matrix. X is the received goods, and W is the sent goods. Simple, huh? What you get, what can you produce, what can you ship out? Okay. So in this matrix, for example, the power station or the power generation plant will have their own internal interdependencies. Okay. That's what these diagrams show here. Okay. But at the same time, the power station will depend on the water station through these elements here, that these little Ys that you have there. These are representative components that say there is an interdependency between power and water, and an interdependency between power and roads to make that thing. So then you develop that, solve that mathematical problem, and then ta-da, you have a very effective way of looking at that problem. Okay? So we use very advanced, sophisticated techniques to solve very highly nonlinear problems, but at the end, what we have is a tool that can analyze these situations in a very, very fast way. Okay? And for example, a system with 3,000 cells, 3,000 infrastructures, with 15 inputs and outputs each one, to simulate a 10-hour scenario at 5 minutes steps in the scenario, it just takes an hour or two to do this simulation. Okay? And of course, it's an approximation, but here's an idea of how the results are looking at. For example, this is how the water system, this is for the UBC hospital, how the water will come to the hospital, the doctors, at what point the doctors will be able to come to the hospital, because you have no doctors, no way to treat patients. Okay? So, and then we start looking at doctors, nurses, medicines coming, at what point you don't have enough medicines, the hospital cannot operate as expected, so you have to wait for medicines to come, number of beds that you can produce. Typically, hospitals are how many beds they have, and how many patients they can treat, etc. So that starts giving you a sense of how you're going to recover your operations through these simulations. You can also do what-if analysis. For example, this is the real world, and let's say in this simulation you make a decision and you want to see what is the effect of your decisions. You have no action, you don't make any decision, it goes this way. You make another decision, and then you can go through all these branches. And that's why the simulator is essentially, as I was saying, related to what flight simulators are doing, developing a number of scenarios that can be used for that case. Briefly, to show you how this is being used, we took the UBC campus, because it's a small city. We have about, now today, 50,000 people on a day-to-day. Number of buildings. It's a city in itself. It has all the facilities. So we did a study for that. So we started looking at the campus network, for example, the electrical network, the gas network. We catalog all of that. The fiber network in the campus, we start looking at that. Then we start looking at the damage assessment of buildings on campus for different levels of intensity. And you see, as the intensity starts growing up, the buildings are starting to have problems. But right now, we have not connected that to the interdependencies. All right. Then we start looking also at where are the decision makers, okay? And which buildings are they occupying, okay? And the office of the president, I will not show you where it is, but you might know it, is in one of the buildings that probably will have serious damage. And where are the people that control the emergencies in people, the emergency response group, where are they located with respect to campus? So we start looking at these elements that are part of the critical infrastructure, the decision makers, okay? Then we also look at the possible casualties if the earthquake happens at 2 in the afternoon or at a later time. At 2 in the afternoon, most of the students will be on campus. At 2 in the morning, most of the students will be at the pubs and having fun. So that changes the picture, right? And then we start also looking at the building functionality. Okay. Now let's see how the water system interacts with the building functionality. Okay. Just to illustrate the process of interdependencies. So here we have the water system network, the expected losses from the water system, pipes breaking, etc. And if you just put the two, one on top of each other without looking at the interdependencies, this is how the map will look like. Okay? The level of damage to the buildings, okay, in functionality, and the number of water losses that are expected in all the pipelines. You don't know how the buildings are being affected. But once you include data interdependency, you can see that the picture has changed significantly from this to this. More buildings have become non-functional because they don't have water. As simple as that. Okay, the last example is the hospital at UBC, okay, because it's a critical component in Vancouver, and the hospital depends on the steam, water, electricity that goes to the substation, and then a substation feeds into the hospital. Okay? So if we look at the hospital functionality by itself, you might be looking at this dotted line. Okay? But once you start building the interdependency of that hospital to electricity and water, then you can see that the functionality is very different. Okay? And that is a very valuable tool because then you start seeing why is that this is coming from this one to this one and what you need to prevent this from happening. Okay? And this is how we are using this information. Okay. The last topic that I wanted to present to you is the most recent development that we have in BC. It's a collaborative effort between the BC Ministry of Transportation, UBC, the Geological Survey of Canada, and the BC Ministry of Education is coming up into the picture. And the idea is to develop internet-based tools to monitor earthquakes, not only to find out the level of shaking, but also to find where the earthquake has affected, the effects of the earthquake, how structures have been performed, because there are a number of structures that have been instrumented. We are targeting 40 bridges with the Ministry of Transportation. So far, we have 12 bridges already instrumented. 4 are already online. I'll show you in a moment how this works. The plan is to instrument also at least 40 to 50 schools in the province to monitor earthquakes. And also, we're currently developing an earthquake warning system as a collaborative effort between the 3 organizations to build that picture. And essentially, the Ministry of Education is interested in putting an earthquake warning system in the schools so teachers and children can at least start reacting if an earthquake happens, etc. So let me see if this works. I'm going to go to the internet. It's very short. Okay. So here is BC. Okay, and all these little dots that you have here are essentially stations that are connected to the internet. The circles are ground stations that are monitored by the Geological Survey of Canada, and the little squares are bridges that have been instrumented. Okay. So, for example, you can look at the earthquake activity in the last 24 hours. well, you see the dots change color, but you want to find out whether that's an earthquake or not, because the instruments are collecting information all the time. You just look at this record here, and you're going to find that the record is, everything is real time right now. Okay, it's not an earthquake record. It's somebody probably is in school that the janitor kicked the instrument when he was taking the brooms out of that, and here is that little spike, and that generated that record. But the record is there, and of course, if an earthquake happens, then you have the ability to look at that. We have also done a number of scenarios. Okay, for example, we have simulated a number of historical earthquakes. Let's say we also simulate an 8.2 earthquake in Cascadia, and here you have the shake map that shows the distribution of damage or the intensity, and this is essentially to verify the system. The squares that you have here are the bridges that are already online that could record information, and if you click on one of these things, it will bring you into the site of the bridge that contains information, etc. So the idea is to generate instant information. In this case, the Ministry of Transportation will use that to identify where are the bridges affected by that earthquake and go and inspect those bridges right away and make a decision whether or not the bridge needs to be closed or not. And if the bridge is instrumented, UBC will be responsible for issuing a report to the ministry within the hour of the earthquake and tell them what we saw on the bridge and what's the status of that. Okay. The website is available. Okay, you can take a look at that. We like to encourage you to visit that site and give us feedback, because this is information that is going to be open to the public. There is another level of information that is restricted to engineers, etc. But for the public, this is what we are doing, and the accomplishment is shown there. So with that, I'd like to thank you and just conclude by saying that when you take interdependence into account, they can help you develop more realistic programs for risk reduction and emergency response plan. Okay, this is we have developed methodologies that are useful for the identifications of regions of high risk and how these interdependencies are impacting that region. Tools like the BC-SIMS program or the I2SIMS, the simulator, are powerful tools that are bringing us to a next level of understanding earthquakes and how we understand information and what decisions need to be made. And essentially what we're talking about is disaster resilience, how we build resilience in our communities. But never forget that the first priority in disaster situations is human survivability, and this is what we are trying to first address. Thank you.
Okay, Miraz, if I can have you come and set up. Questions for Carlos?
Again, Tom Schultz from RSA. I find this really interesting because we've been looking at Vancouver and trying to assess the interdependencies. And certainly my boss who's lived there has raised a couple of other points, and I'm just wondering if it's in terms of your BC-SIMS model. In Vancouver, if you had an earthquake, I believe there's a dam there that could possibly rupture. And then if the dam went down and if the ground shook, both of the bridges would go out. And then the infrastructure of Vancouver in terms of the electrical infrastructure, there's transistors on every wooden pole on the corners. When you're doing an assessment like this, do you think of those types of factors too?
Yes, that's the whole idea, to start building the whole infrastructure into that. Not only look at individual components, but let's look at where is that critical infrastructure and how the consequence of that failing, what will be the case, right? Because if we are looking, for example, the Kendall earthquake, it will do nothing to that reservoir in the North Shore. Yeah, or the Subduction earthquake, but if we have the earthquake in the Strait of Georgia, that's a different picture, right? So that's what we are trying to develop, those pictures that will tell us what are the hotspots and what actions need to be taken to minimize the risk. Yeah. That's the whole idea. Yeah. Thank you.
Another question?
Yeah, actually. Just a related question. I was speaking with somebody at lunch about this. As far as I know, along the Fraser River Valley, there is the various dikes there, and those are susceptible to a major flood event, like a 100-year flood. And I was asking the person at lunch whether those would also, the failure of those would also be susceptible from an earthquake perspective, and if that's something that, well, A, does that risk exist, and if it is that something that you would take into account with this work here?
Yes, the risk exists. City of Richmond has been looking at that problem. There has been an ongoing effort in there to solve the issue with the dikes. It's a concern, and then but the models incorporate that effect, right? Because otherwise we will issue in a different picture, right? What we are accounting is whether the dikes have been retrofitted or they have been improved to minimize the failure that might occur there. But the answer is yes. Yeah, we have the. Do we know exactly what to do? No, because we're still looking into the problem. Yeah. But that's a concern for Richmond. Yeah.